Hello again. Let's get started. Let's look at this example here where my cursor is. D by dx of x e to the x. Remember, by the product rule, you do x times the derivative of e to the x, and then plus e to the x times the derivative of x. We left the first guy alone and derivated the second guy, and then plus the other one where we leave the second guy alone and derivate the first guy. And really, by commutativity, it doesn't really matter. You could put the e to the x in front, and make it your first guy, but we won't dwell on that. So now remember, d by dx of e to the x is just itself e to the x. So we just have x times e to the x here, and I put this times sign here for neatness. And if you write this on pencil and paper, you don't necessarily have to put this times sign. You can create a space. You can just do that, actually. Yeah, that's fine. That times sign was actually superfluous. So I have x e to the x, and then plus, and then now e to the x times. Now, guys, d by dx of x is just 1, and 1 times e to the x is just naturally e to the x. So there's that, and we're done. Now, you can stop here. Your professor, I'm sure, would take this. I'm quite confident they would. Or they would probably have no problem at all if you factored out e to the x and got x plus 1 here. You need to be able, I just want you to be able to recognize that these two are the same. Pick whichever one is your favorite. You can stop here, or you can go all the way and put this guy. You may eventually run into an ABCD test where, they don't give you this choice, they give you this choice. But really, they're the same anyway. You just have to recognize that you can factor out an e to the x and get x plus 1, okay? So there's that. Now the next one, d by dx of x e to the x minus e to the x. Here we got a combination of the product rule and the add subtract rule. Again, by the product rule, we again, just as before, we take care of x e to the x first. Again, for the same, just like before, we get x times the derivative of e to the x plus e to the x times the derivative of x. But then we have to do minus, and then minus the derivative of this e to the x. Okay? Well, let's see what happens. Now, so here again we get, this times sign is actually kind of superfluous, so I'm just going to get rid of it. Now, guys, and let me space down to get everything on one line here. So what we got, now remember, d by dx of e to the x is just itself e to the x. So there's that. So we have x times e to the x, then plus, and then we have e to the x times 1, but that's just e to the x himself. And then minus e to the x again. The derivative of e to the x is e to the x. But hey, lo and behold, we got a plus e to the x here and a minus e to the x. So the next thing that's going to happen is these are going to cancel. And that just leaves x e to the x all by himself. So there's that, and we're done. Later, we're going to come back to this guy. Later, when we do the so-called antiderivative of x e to the x, we're going to end up with x e to the x minus e to the x plus some constant. But anyway, we're going to use this later to do what we call the antiderivative, where we do the antiderivative of x e to the x, and we pretty much get x e to the x minus e to the x again, but we have to put a plus constant there. But we'll talk more about that later. That's just a heads up for things to come later on. So let's move along. Now, let's look at this guy right here. The limit as h goes to 0 of, this looks awful strange. This looks pretty complicated. We got the cosine of this guy minus radical 2 over 2 all over h. But now here's the thing. The trick is to recognize that radical 2 over 2 is the cosine of pi quarter. But even then, we may be a little bit foggy. We're like, well, Jason, how do I do that? That limit's kind of nasty. Don't do the limit. Remember, we're doing the derivative. This is what's going on here is if f of x is cosine x, we are doing f prime of x evaluated at pi quarter. So all we're really doing is we're derivating the cosine of x first, and then after the fact, we're throwing in x equals pi quarter. So we just do the derivative of the cosine. Uh-oh, I did kind of mess up. I forgot my negative. That's the negative sign. Sorry about that, guys. I forgot my negative. Oopsie. So, oops. And then let me put my negative. So the final answer is negative radical 2 over 2. And I'll save this here in a second, and I'll replace my documents in Udemy and all that. Sorry about that. I made a minus sign boo-boo there. And I made the same goof down here. I need to change this. And so let me change this guy right here. And that's going to change this guy right here naturally. So let's do another example. If I do 1/2 instead of radical 2 over 2, well, the trick is to remember that 1/2 is the cosine of pi thirds. So we're just doing elf prime at pi thirds. Elf of x is cosine x, and we're just doing elf prime at pi thirds. So we're derivating the cosine of x first, giving us the negative sign, and then after that we're throwing in pi thirds. So we have the negative sign of pi thirds, and that by trigonometry, that's going to be negative radical 3 over 2. And I also deployed trig here when I got the negative radical 2 over 2. But anyway, so the point is we can use what we already know to make some nasty limits not so nasty. We can make them doable. You know, something that would have been hard to do is now much easier to do. Okay, and let's see. Here we make a little note. What do we say here? Note that this guy right here, this is kind of awkward to write every time. A lot of textbooks, probably most, would write this as the cosine prime of pi quarter, but that's as long as no confusion arises. This can be dangerous because if you're in a situation where there's more than one variable, this can leave you in the dark. This right here leaves no ambiguity. This does, even though it's much more cozy to write. So as long as no confusion arises, and as long as it's okay with your professor, you can do it this way. Ask your professor first before you go off and start writing it like this, okay? Let's go down here and look at another example. Let's move along. Now, here's another nasty limit. But remember, this is the fifth power. This is just f of x is x to the fifth here, and we're evaluating things at x equals 3. Imagine instead of 3's here, we have x's where these 3's are. So what we're doing is we're doing the derivative of x to the fifth, and then after the fact, we're throwing in x equals 3. Remember, the derivative of x to the fifth is 5x to the fourth, but now what we're doing is we're throwing 3 in there, so it's 5 times 3 to the fourth. Order of operations, you go ahead and do the 3 to the fourth, you get the 81, then multiply by 5, you get 405. And guys, that's notice we're using what we already know to make limits that would be very tough, fairly simple to do. So there's that. It's nice when we can, use this and do that sort of thing. Note that x, if we'd have written it like this, that would be more awkward. I may avoid the prime notation unless it is very obvious what I mean. If you're ever going to write it like this, and then I don't really count the prime notation, let's just not, okay? Ask your professor in any event if you just love what you see with this prime notation, but I would recommend just not doing it, or at the very least ask your professor. Okay, let's look at this guy right here. The limit as x goes to 1 of this guy. Now, here's the thing. What are we doing here? Now this limit would be a weird one to do as well. It would be a 0 over 0 limit. But let's see if we can use a shortcut. Notice what we're doing. We're doing d by d. This is just the derivative of this numerator evaluated at x equals 1. So we do the derivative, and we would get 7x to the 6 minus 3. But we throw in 1 in for x, so we have 7x to the 6, but x is 1. You do need these parentheses here just for good manners. So that's 7x to the 6 minus 3, where I throw 1 in for x. Okay, x is 1, because we're here, x is general. Here, x is, we're replacing, this is telling us to go ahead and do the derivative, get 7x to the 6 minus 3, and then throw 1 in there. Okay, in for x, replace x with 1. But hey, now guys, 1 to the 6 is just 1, and 1 times 7 is just 7. The 7 just stays put, so we just get 7 minus 3, and that's 4. And if we go down and do this guy like that, notice this is, we just do the derivative of that numerator with respect to x. You do the derivative first, as always. Now that's 4x cubed minus 10. and then, but you throw 5 in place of x. So we have 4 times 5 cubed minus 10. And remember PEMDAS, you do the 5 cubed, you get 125, multiply by 4, you get 500, then subtract 10, and you get your 490. Okay. See how nice of a shortcut that is? These problems would not be fun without, the derivative. But anyway, moving along. Let's look at this guy right here. The limit as x goes to -1 of this numerator over x plus 1. Again, we do the derivative, and we're going to throw in -1. So that's 7x to the 6 minus 3, but this time we're using -1. And I hate it when it skips lines like that, so let me move that down. So we're going to have 7x to the 6 minus 3, but you got to throw parenthetical -1 in the place of x. And then we've been doing the parentheses all along anyway. So, but again, now -1 to the 6 is +1, and +1 times 7 is still just 7. So it's 7 minus 3 equals 4. And there's that. And so I just want to show off that useful tool, okay? Now let me just type in recall. We're kind of changing gears here, and I didn't really indicate that too well. So let's move away from that now, and let's do a recall. Recall that d by dx of x to the 4th minus 3x squared, that's 4x cubed minus 6x. And recall d by, now we don't have to, we've been using x the whole time pretty much, more or less, just about. You can use other letters, guys, as your independent variable. We could do t. d by dt of t to the 4th minus 3t squared is 4t cubed minus 6t. That's just to show off that you can use other letters, So there's that. And now here's a nasty problem. And again, now the times sign, is it crucial? No, but Word, remember Microsoft Word puts this 2 and this 5 way too close together. This times sign is annoying to have to look at. It's an eyesore, and on pencil and paper you don't have to write it, but on Word I kind of did. I could create a space like that. No, not like that. Like that. But now that, to me, that looks funny too. So let me just put that times sign back there. So I'm doing d by dx of x squared times the 5th root of x, and then separately minus 8 times the 9th root of x to the 4th. And to me, even that 8 and that 9 are too close together. So let me put another times sign. Okay, and I don't like how this thing skips lines on me. So what are we going to do? Let's do that. Let me get this thing at least a line better. So we do, remember, now here I do a little algebraic trick. Remember, x squared can be thought of as the 5th root of x to the 10th. So I replace this x squared here with the 5th root of x to the 10th. Remember, by the radical laws, as long as x is positive, well, actually it doesn't even matter here anyway, but let's just assume x is positive. 10 divided by 5 is 2. So that's 2 there, okay? So x squared is the same as the 5th root of x to the 10th. So the 5th root of x to the 10th times the 5th root of x, and then minus 8 times, and yeah, let me put my times in there, the 9th root of x to the 4th. So what have I got? Now remember, the derivative of the difference is the difference of the derivatives. Hey, I can combine, but wait, before we even talk about that, let's not even talk about that yet. It's not time. Remember, these are the same type of radical, a 5th root and a 5th root. We're assuming x is positive. Actually, we don't, since it's odd root, we don't have to make that assumption. But anyway, let's just go ahead and make that assumption anyhow. So assume x is positive, even though we don't have to for the 5th root. So now x to the 10th times x to the 1 is x to the 11. So I can bring these two guys in together as x to the 11. Remember, you have to multiply before you ever add or subtract, even if you can add and subtract. So we have the 5th root of x to the 11. And then on the other side of the minus, separately, we have 8 times the 9th root of x to the 4th. And again, I don't want you to go off thinking that's 8 to the 9th power. Well, unfortunately, it forced me to skip line. I hate it when it does that. So I have a skip-a-roo there. But anyway, so I've done my do there. I've got that 5th root of x to the 11. But now here's the deal. let's go now. Aha! Let's get out of radical form and go to exponent form. Remember, the fifth root of x to the 11th, that's x to the 11/5. And remember, the ninth root of x to the 4th, that's x to the 4/9. Okay, so we're doing d by dx of all that. And then it does a line break on me again, which I hate. So we actually, now finally we can go in and execute this derivative right here. And we get the 11/5 comes down, 11/5 x to the 6/5. Because remember, 11/5 minus 1 is 11/5 minus 5/5, which is 6/5. And then that 8 just sticks on. And remember, we bring the 4/9 down and multiplies into that 8. And then I subtract 1 from 4/9 and I get negative 5/9. Okay, but remember, guys, this 8 multiplies this 4 right here and I get 32. So that's just 32 over 9. We don't mess with the 9. So I don't mess with this guy, and then I get minus 32 over 9, x to the same power. Okay, and then it skips a line on me again, so let me move this down. So what comes next? In general, a lot of times your textbook and your professor will want you to get positive exponents, or a lot of times they'll want you to go back to radical form, in fact. But anyway, let me get my spacing back here. Okay, so we've done this part. Now we got to go back to radical form. So we have 11/5 x to the 6/5. Now, guys, here's a trick. Remember, x to the 6/5, that's really x to the 1 times x to the 1/5. Because what you're doing there, let me create, I kind of skipped that step, and that might cause some confusion among some of my students. So lest there be any mistake, what I'm doing is that x to the 6/5, I'm writing that as x to the, by the law of exponents, x to the 5/5, which is just x to the 1, times x to the 1/5. And then that x to the negative 5/9, I'm not messing with it yet. So let me do that. And then by the law of exponents, well, actually, no, that's good. I've done what I needed to do. So I broke up 6/5 as x times x to the 1/5. So we have 11/5 times x, and going back to radical form, by definition, x to the 1/5 is the fifth radical of x. And I have this times sign here on a kind of Microsoft Word. On paper, you can just slap them together. And then minus, now guys, remember, by the law of exponents, x to a negative power goes in the bottom. So that x to the negative 5/9 goes down there with that 9. So as x to the positive 5/9, but it's on the denominator now. It was in the numerator when it was the negative power. So we have all that. Now, here's the trick. We're happy with this guy. So we have 11/5 x times the fifth root of x as before. But then minus, we don't like a fractional power on the bottom. That's indicative that we have a radical on the bottom, which we don't particularly like. So now the question to ask yourself is 5/9 plus what power is 1? Well, the question to ask is 5/9 plus what is 9/9? 5 plus what is 9? Namely 4. So 5/9 plus 4/9 is 9/9, but 9 over 9 is 1. So we stick x to the 4/9 down here, but the price we got to pay is we have to stick x to the 4/9 up here. Okay? Now by associativity, we can go ahead and multiply this x to the 5/9 times x to the 4/9. That's just x to the 9/9, but that's x to the 1, but that's just x himself. So there's that. And that x to the 4/9, that's the ninth root of x to the 4th by definition. And then here's my other stuff from before. And guys, that's it.